A corroded lump of bronze sat on a museum shelf for decades. It was pulled from an ancient shipwreck, looking like a piece of sea-rotted junk. But this unassuming object, known as the Antikythera Mechanism, is now considered the most sophisticated scientific artifact from the ancient world. Modern imaging has revealed it to be a labyrinth of precise bronze gears, a mechanical computer built over 2,000 years ago. This device does not fit our story of technological history at all. It is a profound anomaly, a ghost from a past we thought we understood. By the end of this journey, you will see how a single discovery is forcing us to rewrite the history of human ingenuity. We will uncover its purpose as a cosmic calculator, meet the geniuses who might have built it, and confront a haunting possibility. Was this intricate machine a miraculous one-off, or is it the sole surviving witness to a lost era of Greek computing, a whole chapter of advanced science that vanished from memory? What does it mean when history forgets its own brilliance? The seafloor near the tiny Greek island of Antikythera is a steep underwater cliff plunging into darkness. In the spring of 1901, a crew of sponge divers was sheltering from a storm in those waters. Seeking a safer spot to wait, their captain sent a diver named Elias Stadiotis down to scout the seabed. He descended along the cliff face past 50 meters, a depth far beyond normal diving limits of the time. What he saw in the dim blue light was not a safe harbor, but a haunting scene. Marble limbs and bronze bodies lay scattered across the sand, as if a gallery of gods had been shattered and left in the deep. Stadiotis surfaced in a panic, convinced he had seen a heap of drowned corpses. He was, in fact, the first person in over 2,000 years to lay eyes on a royal Roman shipwreck, a vessel that had been carrying a fortune in Greek art and luxury goods back to Italy. The subsequent salvage operation was perilous and primitive. Divers worked without modern breathing apparatus, risking paralysis and worse from the bends as they hauled up breathtaking bronze statues, exquisite glassware, and marble sculptures. It was a treasure hunter's dream, a trove of classical beauty. Amidst this harvest of art, a lump of heavily corroded bronze and wood, about the size of a large dictionary, was also pulled from the mud. It was catalogued vaguely and set aside, utterly overshadowed by the more visually stunning finds. To the archaeologists of the day, it was an unidentifiable, crusty mass, perhaps a piece of navigational equipment or a badly damaged statue fragment. Its true nature was hidden beneath centuries of mineral deposits. The mystery began to crack open only months later, when the object dried and split apart. Inside, someone saw a glint of metal and the faint trace of an inscription. Upon closer inspection, the team made a bewildering discovery. Embedded within the corrosion were precise, toothed gear wheels. This was not a statue, it was a machine, and the inscriptions were in ancient Greek. The immediate reaction was one of profound chronological confusion. Intricate geared mechanisms belonged to the clockwork of the Renaissance, not the classical world of philosophers and poets. It was as if excavators at a medieval castle had uncovered a smartphone. The artifact was so technologically out of place that some scholars initially argued it must have fallen from a much later ship, a theory the unified wreck site quickly disproved. From its very first moment in the modern world, the Antikythera mechanism presented a single, unavoidable question. What was this complex device with its miniature bronze galaxies doing on a Roman cargo ship loaded with sculptures and silver? The answer would require not just digging in the earth, but a journey into the deepest layers of forgotten knowledge. For decades, the mechanism's fragments sat in a museum in Athens, a puzzle with no clear solution. Early researchers in the 1900s could only work with what they could see on the surface, which was not much. The bronze was encased in a thick, greenish crust of mineral deposits, a hardened shell formed by 2 millennia under the sea. Peering at the cracked pieces, scholars could just make out the outlines of those mysterious gears and the faint, ghostly traces of Greek letters. But without a way to see inside the calcified block, their theories were educated guesses at best. The most common early hypothesis was that it must be some form of astrolabe, a well-known instrument for measuring the positions of stars. But even a basic astrolabe did not require a complex system of interlocking bronze gear wheels. Another suggestion was that it served as a navigational tool for the ship that carried it. Yet the mechanism's delicate construction, with its finely cut teeth and intricate plates, seemed ill-suited for the rough, practical life of a sailor. It was more like a philosopher's instrument than a mariner's tool. These initial interpretations fell short because they were trying to fit the object into a box that simply did not exist. The Antikythera mechanism refused categorization. It was quite literally one of a kind, with no parallel in the entire archaeological record of the ancient world. This very strangeness is what transformed it from a curious artifact into a century-long detective story. The first investigators knew they were looking at something extraordinary, but the full magnitude of its secrets was locked away, hidden beneath layers of time and corrosion, waiting for a new kind of light to reveal its truth. The real breakthrough came from a technology the device's creators could never have conceived. By the late 20th century, researchers were no longer limited to what their eyes could see on the surface of those green, crusted fragments. They turned to tools from the world of medicine and engineering, aiming a new kind of vision at the ancient bronze. The first major leap was the use of gamma-ray and X-ray imaging in the 1970s. Like a doctor taking an X-ray of a broken bone, this technique allowed scientists to peer through the outer crust and map the ghostly outlines of the internal gearwork. For the first time, they could begin to count the gears and trace their connections. It was a revelation, confirming that the complexity inside was even greater than anyone had dared to guess. But X-rays had their limits. They produced a flattened, two-dimensional shadow of the three-dimensional object, making it difficult to understand how the gears meshed together in space, or to read the inscriptions that were buried within the calcified layers. The puzzle needed a deeper look. That deeper look arrived with the dawn of the 21st century and a technique called microfocus computed tomography, or CT scanning. You have likely heard of CT scans in a hospital context, where they create a detailed three-dimensional model of the human body, slice by tiny slice. Researchers applied this same principle to the Antikythera fragments. The machine took thousands of high-resolution X-ray images from every possible angle, and powerful computer algorithms then stitched them together into a perfect digital model. This was the ultimate key. Suddenly, scientists could virtually peel away the 20 centuries of corrosion like layers of an onion. They could rotate the mechanism in space, examine each gear tooth individually, and even read Greek text that had been invisible since the day the ship sank. The CT scans revealed an astonishingly precise machine. They counted not just a few gears, but a sophisticated system of at least 30 interlocking bronze gear wheels, some with teeth cut as fine as 1 millimeter. They mapped intricate dials on the front and back, and most importantly, they recovered hundreds of new characters from the explanatory inscriptions etched onto the plates. This flood of data was the turning point. The Antikythera mechanism was no longer just a curious fragment to speculate about. It had become a decipherable text, a detailed instruction manual written in the language of mathematics and mechanics. The raw architecture of an ancient computer was now laid bare, waiting for its code to be cracked and its purpose to finally be spoken aloud. The CT scans provided the blueprint, but the inscriptions etched onto the plates delivered the user manual. As researchers painstakingly translated the ancient Greek text, the device's stunning purpose came into sharp focus. This was not merely an instrument, it was a cosmic calculator. The Antikythera mechanism was designed to model the complex, dance-like motions of the heavens with astonishing precision. Its primary function was to predict the phases of the moon, the timing of solar eclipses, and the ever-shifting positions of the 5 planets known to the ancient Greeks: Mercury, Venus, Mars, Jupiter, and Saturn. Think of it not as a telescope for looking at the stars, but as an intricate, hand-cranked simulation of the solar system. You would turn a handle on the side, and as the gears meshed and spun, a series of pointers on multiple dials would advance, showing where each celestial body would be in the sky on any given date, years or even decades into the future or past. It ran on the astronomical theories of its time, particularly the work of Greek thinkers who believed the sun, moon, and planets moved in perfect circular orbits around the Earth. The machine's genius was in its mechanical translation of these mathematical theories into physical motion. One of its most sophisticated features was its ability to model the moon's irregular orbit. The moon does not travel around Earth at a constant speed. It speeds up and slows down in a predictable cycle. The mechanism replicated this not with a simple gear, but with a brilliant assembly called a pin and slot device, a differential gear system that subtly varied the moon pointer's speed to match the cosmos itself. This was a mechanical realization of abstract astronomy, a universe in miniature made from bronze and human ingenuity. It served as a powerful demonstration tool, likely for teaching, for philosophical inquiry, or for planning important civic and religious events tied to celestial cycles. In essence, someone could hold this box and witness the logic of the cosmos turning at their fingertips, a silent, ticking oracle of the sky. The genius of this machine is found in its silent, ticking heart, a complex assembly of interlocking bronze gear wheels known as a gear train. This was not a simple clockwork. It was a physical model of cosmic mathematics, where every turn of a gear tooth represented the movement of a planet or the passage of a month. At the center of this miniature universe was an input shaft, likely turned by a small hand crank. As you turned that handle, you were not just moving metal, you were setting the entire known solar system into motion. The crank drove a central gear, which then engaged with a carefully calculated network of other gears, each with a specific number of teeth. These numbers were not arbitrary. They were the secret code, the mathematical language that translated celestial cycles into mechanical rotation. For instance, one crucial gear had 127 teeth, a strange and prime number. This precise count was the key to modeling the moon's orbit with incredible accuracy, matching a ratio refined by Babylonian astronomers centuries before. The gear train branched out like the roots of a tree, each pathway dedicated to a different celestial body, calculating their positions through a symphony of synchronized bronze. Perhaps the most astonishing component within this ancient computer is a device called a differential gear. Modern engineering did not see such a mechanism again until the 16th century, inside sophisticated European clocks, and then later as the core of every automobile's axle system. Its purpose is to combine two inputs of motion into one smoothed output, or to allow for a difference in speed. In the Antikythera mechanism, this ingenious assembly was used to model the moon's variable speed as it orbits Earth. The moon does not travel at a constant pace. It appears to speed up and slow down in a predictable cycle. To replicate this in bronze, the maker used a small gear with a pin that slid within a slot on a larger gear. This pin and slot system subtly varied the rotation, making the pointer for the moon on the front dial accelerate and decelerate just as the real moon does in the sky. It was a stroke of mechanical genius, a physical solution to an astronomical problem that shows a profound understanding of both observation and engineering. This marriage of mechanics and mathematics reaches its peak in how the device tracked time itself. The gear ratios were deliberately chosen to encode long astronomical cycles discovered not by the Greeks, but by even earlier Babylonian sky watchers. One of the most important is the Metonic cycle, a period of approximately 19 solar years, which equals almost exactly 235 lunar months. This cycle was the foundation of many ancient calendars, as it kept lunar and solar years in rough alignment. The mechanism's gearing incorporated this 19-year cycle, allowing it to show the current phase of the moon and its position in the zodiac for any given date across decades. More dramatically, it also encoded the Saros cycle. This is a period of about 18 years and 11 days after which the Sun, Moon, and Earth return to nearly the same relative geometry, causing a similar pattern of solar and lunar eclipses to repeat. By turning the crank, a user could advance through time and see when the next potential eclipse would occur, marked by a glyph on a special dial. This was not magic, it was predictive science hardwired into bronze. The Antikythera Mechanism stands as a perfect fusion of global knowledge, Babylonian arithmetic, Greek geometry, and a breathtaking mastery of precision craftsmanship. It represents a moment in history where the abstract patterns of the cosmos were not just written on papyrus, but forged into a machine that could hold time in its hands. The front face of this ancient computer was its breathtaking display, a window into a moving cosmos. Reconstructed from the CT scans and inscriptions, we can now see its primary user interface. At its center was a large, round dial, divided into concentric rings like the layers of an ancient tree. The outermost ring displayed the 365-day Egyptian calendar, a simple and stable system the Greeks used for astronomical calculations. Inside that, a second ring was marked with the 12 signs of the zodiac, the band of constellations through which the Sun, Moon, and planets appear to travel. Two elegant pointers, likely fashioned as small hands, moved around these dials. One represented the Sun, its golden tip tracing a year-long journey through the zodiac. The other, a silver pointer, marked the Moon's faster monthly circuit. By turning the hand crank on the side, an operator could watch these pointers advance in perfect harmony, showing the precise positions of both the Sun and Moon in the sky for any chosen date. But the display offered even more wonder. Researchers believe the moon pointer was not just a simple arrow. At its tip was a tiny, rotating ball, likely crafted from ivory or bone and painted half black and half silver white. As the pointer moved and the internal gears turned this miniature sphere, it would have displayed the current phase of the moon, from a gleaming silver full moon to a stark black new moon, and every sliver in between. This tiny model would have mirrored the lunar cycle in real time. The effect must have been magical, to see the mechanical moon wax and wane as you turn the crank, while the solar and zodiac dials spun in sync, was to witness a perfect miniature universe operating under known laws. You could fast forward through time, watching celestial patterns repeat over months and years, or rewind to check the sky on a past date of importance. This was not passive observation, it was interactive astronomy. It transformed complex celestial mathematics into a tangible, visual story, one that could be held in the hands and understood by the mind. While the front dial displayed the living sky, the back of the mechanism held its prophetic power. Here, two large spiral dials, like coiled bronze serpents, contained the machinery's most advanced predictions, bridging the gap between cosmic law and human life. The upper spiral was a masterpiece of celestial forecasting. It modeled the Saros cycle, a period of approximately 223 lunar months, or about 18 years and 11 days. After each Saros cycle, the Sun, Moon, and Earth returned to almost the same geometric alignment, causing a similar pattern of eclipses to repeat. This dial allowed a user to scroll forward through time and see exactly when the next potential eclipse would occur. But it did far more than just mark a date. Tiny inscriptions in the spaces between the spiral's coils provided a detailed forecast for each event. They predicted not only the time of day an eclipse might happen, but its type, whether it would be solar or lunar. Most astonishingly, some glyphs even suggested the likely color of the eclipse based on ancient atmospheric lore. A dark, reddish eclipse might be seen as an omen, while a bright one could be considered more favorable. This transformed the mechanism from a calculator into an oracle. In a world where eclipses were often seen as powerful, disruptive messages from the gods, the ability to predict them with mechanical certainty would have been a source of immense knowledge and perhaps even political power. It demystified the heavens, replacing superstition with a schedule written in bronze. Just below this cosmic calendar was a second spiral dial, firmly rooted in the rhythms of human society. This dial tracked the 4-year cycle of the Panhellenic Games, the great athletic and cultural festivals that unified the Greek world. The most famous of these, of course, was the Olympic Games, held every 4 years at Olympia. But the cycle also included the Pythian Games at Delphi, the Isthmian Games near Corinth, and the Nemean Games. The dial's pointer would advance year by year, and inscriptions in each segment of the spiral would indicate which games were to be held that year. This combination is profoundly revealing. On one side of the same device, you could calculate the next solar eclipse, a fearsome celestial event. On the other, you could plan your journey to attend the Olympic foot races or the poetic contests at Delphi. It seamlessly wove together the scientific and the social, the astronomical and the administrative. The Antikythera mechanism was not locked away in a lonely philosopher's study. It was a practical instrument for managing time in its broadest sense, synchronizing human festivities with the grand, predictable clockwork of the universe. It served as a bridge, reminding its user that the timing of a sacred athletic contest was, in its own way, as orderly and significant as the dance of the moon and sun. The silent bronze of the mechanism was never meant to be silent. Its voice was etched directly onto its body, in thousands of tiny Greek characters that formed a comprehensive user's manual. These inscriptions, recovered letter by letter from the inner surfaces of the plates and even on some of the gears themselves, transformed the device from a mysterious artifact into a speaking witness. This is not decorative script or a maker's signature. It is a dense, technical document, an astronomical glossary and operating guide fused to the machine it describes. The text performs several vital functions. First, it labels the dials and pointers, so a user would know they are looking at the pointer for Venus or the dial for the Olympic cycle. Second, it explains the celestial phenomena the mechanism predicts. Next to an eclipse glyph, the writing might describe the event's duration or its traditional interpretation. Third, and perhaps most tellingly, it includes what we would now call usage notes or help text. One remarkable passage, for instance, explains how to account for a slight discrepancy in the moon's motion, a kind of ancient troubleshooting guide for keeping the cosmic model accurate. This embedded manual is overwhelming evidence that the mechanism was a practical tool for an educated user, not a ceremonial object. It directly connects the bronze gears to the scholarly world of its time, revealing the specific astronomical knowledge it was built to encapsulate. The language is not poetic, it is precise and instructional, referencing the cycles of planets and the structure of calendars with the confident shorthand of a textbook. This tells us the device existed within a living tradition of knowledge. Someone had to write this manual, and someone else had to be able to read and use it. The inscriptions are the bridge between the abstract genius of the gear train and the human hands that turn the crank, a permanent record of the conversation between a maker and a user frozen in time. Who crafted this bronze cosmos? The inscriptions provide the first crucial clue. The language used is a specific form of Greek from the 1st or 2nd century before the Common Era, and the calendar it references points decisively to the island of Rhodes, a powerhouse of science and trade in the ancient Mediterranean. Rhodes was more than just a port. It was a beacon of learning, home to a famous library and a vibrant community of philosophers, astronomers, and engineers. It was the Silicon Valley of its day, a place where abstract theory met practical craftsmanship. This geographical fingerprint leads us directly to two towering figures whose shadows seem to fall across the mechanism's intricate design. The first is the astronomer Hipparchus. Working on Rhodes in the 2nd century before the Common Era, Hipparchus made monumental discoveries. He catalogued the stars with unprecedented precision, developed complex models for the motions of the sun and moon, and is credited with discovering the precession of the equinoxes, the slow wobble of Earth's axis. Most tellingly, his mathematical model for the moon's irregular orbit uses the exact same unique ratio, that 127 to 120, that is physically engineered into the device's gears. It is as if someone took the equations from Hipparchus's notebooks and translated them directly into turning bronze. The second figure is the philosopher Posidonius, a later giant of the Rhodian school. A student of the universe in its entirety, he was renowned for building intricate models and instruments to demonstrate scientific principles. Ancient writers describe a brilliant orrery he constructed, a moving model of the heavens. While no direct evidence ties him to the Antikythera device, he represents the very culture of hands-on experimentation and mechanical illustration that would have been necessary to birth such an object. The mechanism feels like a physical manifestation of the intellectual ferment he embodied. But an astronomer's theory or a philosopher's vision is not enough to create such a device. The breathtaking precision of its construction, with gears cut to sub-millimeter accuracy from sheets of bronze only 1 or 2 millimeters thick, speaks of a different kind of genius. This points us away from a lone inventor and toward a collaborative workshop. Imagine a small, specialized atelier in Rhodes, a place where the scent of hot metal and beeswax for casting filled the air. Here, a mathematician would have provided the complex gear ratios and astronomical cycles. An astronomer would have supplied the observational data and celestial theories. And a master artisan, a virtuoso of the lathe, file, and drill, would have translated those numbers and concepts into a tangible, functioning machine. This was not mass production. It was a bespoke fusion of the highest abstract thought and the most refined manual skill. The Antikythera mechanism, therefore, is not some magical alien artifact. It is the logical, if spectacular, product of a specific time and place, a golden moment where the right knowledge, the right craftsmanship, and the right culture of inquiry converged on a small island in the Aegean Sea. It is a testament to what happens when the greatest minds of an era are not just thinking about the cosmos, but are determined to build a working model of it. But this single, surviving masterpiece presents us with an immense and unsettling puzzle. If this technology was so advanced, so brilliantly realized, where are all the others? The complete absence of any similar device from the ancient world is a silence that rings louder than any discovery. In all the excavations of Greek and Roman cities, from grand libraries to humble workshops, not one other geared mechanism of this complexity has ever been found. The literary record is just as barren. While ancient texts celebrate great statues and paintings, they offer only the faintest, most ambiguous whispers about machines like this. A passing mention by Cicero of a bronze sphere that showed the motions of the heavens, a cryptic line in a poem. These are fragments that only deepen the mystery rather than solve it. This profound absence forces a critical question. Was the Antikythera mechanism a miraculous one-off? A stroke of genius that flashed into existence and then vanished without a trace? Or does its very sophistication tell a different, more haunting story? To build something this perfect, you do not start from zero. The intricate gear trains, the precise mathematical ratios etched in bronze, the flawless craftsmanship, all of it points to a tradition. It implies a lineage of trial and error, of workshops where knowledge was passed from master to apprentice, of a gradual refinement of techniques over generations. You cannot invent differential gearing in a vacuum. The existence of this device strongly suggests there were simpler models that came before it, and perhaps even more complex ones that were lost. It hints at a whole school of mechanical philosophy, a path of technological development that history simply forgot. We are left staring at this lone survivor, wondering if it is not an anomaly but a relic. A single, battered page torn from a vast and sophisticated book of knowledge that was closed, its contents scattered to the winds of time. This is the central, chilling mystery of the Antikythera mechanism. It is not just a machine, it is a ghost, and its presence suggests an entire ghost era of Greek science and engineering, a lost chapter in the story of human ingenuity that we are only now beginning to suspect ever existed. The silence of the archaeological record is not quite absolute. If we listen closely, we can hear faint echoes of this lost craft in other places, whispers that suggest the Antikythera mechanism was not a solitary island of genius, but perhaps the highest peak in a forgotten mountain range. Our first clues come not from the ground but from surviving texts. The Roman philosopher and statesman Cicero, writing in the 1st century before the Common Era, describes a remarkable device. He mentions a bronze sphere built by the philosopher Posidonius, which, when turned, showed the motions of the sun, moon, and 5 planets with each passing day, exactly as the heavens themselves displayed them. The description is uncanny. It matches the function of the Antikythera device so closely that many believe Cicero was describing either an identical machine or one from the same tradition. Another writer, centuries later, briefly refers to a gift sent by the engineer Archimedes to Rome, a portable planetarium that demonstrated eclipses. These are not detailed technical manuals, they are passing remarks in philosophical works, the kind of casual references one makes to something they assume their audience already understands. This is key. The writers were not announcing a shocking new invention. They were alluding to known marvels, objects so extraordinary they had become legendary, yet their underlying technology had already faded from common knowledge by the time these words were penned. Beyond these literary ghosts, we find tangible proof that the Greeks possessed the mechanical sophistication to build such things. Look to the work of Heron of Alexandria, an engineer of the 1st century. He did not build cosmic calculators, but he authored entire books on mechanical principles and constructed astonishing automata. He described and built self-opening temple doors powered by steam, a wind-powered organ, and intricate mechanical theaters where small figures performed entire plays driven by a system of ropes, drums, and simple gears. These were not toys, they were public demonstrations of mechanical philosophy, proving a deep, practical understanding of how to translate energy and information into precise motion. Even more widespread was the use of gearing in water clocks, known as clepsydry. These were not simple buckets with a hole. Elaborate versions used a constant flow of water to turn a gear train that would move a pointer across a dial to mark the passing hours, sometimes even triggering bells or moving figurines. The basic components, the axles, the tooth-cut wheels, the principles of transferring motion, all of this was known and practiced. The Antikythera mechanism did not invent gearwork from nothing. It took these existing, well-understood mechanical concepts and applied them to a problem of breathtaking scale and complexity, the simulation of the cosmos itself. What these fragments reveal is a technological landscape far richer than we once believed. The mechanism stands not as a miraculous accident, but as the most spectacular survivor of a rare and elite craft. It represents the ultimate application of a known toolkit to the grandest possible subject. The knowledge was there, the craftsmanship was there, and the intellectual ambition was certainly there. This makes its disappearance not just puzzling but profoundly tragic. It shows us that a path was opened, a brilliant fusion of mathematics, astronomy, and precision engineering that could have changed the course of scientific history. Yet this path seems to have led into a shadow, leaving behind only one corroded key. The genius of the mechanism's gears was not born in a vacuum. Its mathematical soul, the very numbers etched into those bronze teeth, came from a civilization far older than Greece. To understand this machine fully, we must travel centuries before its creation, to the flat plains of Mesopotamia and the temple astronomers of ancient Babylon. For over 1,000 years, Babylonian scholars meticulously recorded the night sky. They did not seek grand theories of cosmic spheres. Instead, they were supreme data collectors. Using simple but consistent methods, they logged the positions of planets, the timing of lunar phases, and every eclipse they witnessed, creating an archive of celestial events that spanned generations. This was not philosophy, it was a practical, almost bureaucratic endeavor, born from a belief that the heavens held messages for earthly kings and the fate of empires. Their legacy was not a model of the universe, but something arguably more powerful, a vast, precise data set of how the sky actually behaved. Centuries later, this treasure trove of observation made its way to the Greek world. When a brilliant mind like Hipparchus of Rhodes sought to create mathematical models for the irregular motions of the moon, he did not start from scratch. He turned to the Babylonian records. His groundbreaking work relied directly on their centuries of lunar observations, which allowed him to deduce the precise cycles, like the subtle wobble in the moon's orbit, that his equations described. This is the hidden foundation of the Antikythera mechanism. When you turn its crank and the moon pointer speeds up and slows down with perfect rhythm, you are not just witnessing Greek engineering. You are seeing Babylonian data in motion. The machine's ability to predict eclipses decades in advance is powered by the Saros cycle, a pattern the Babylonians identified and catalogued long before. The specific odd-gear ratio of 127 to 120 that models the moon's orbit is a mechanical translation of a numerical relationship first spotted in those ancient clay tablets. The device, therefore, represents a breathtaking synthesis of three great traditions. It is built on the bedrock of Babylonian empirical observation, the patient, millennia-long recording of facts. This raw data was then processed through the Greek genius for geometry and theoretical modeling, transforming lists of events into elegant mathematical relationships. Finally, this abstract understanding was realized through the pinnacle of Greek mechanical craftsmanship, forged into a tangible, turning model of the cosmos. The Antikythera mechanism is a monument to collaborative knowledge across time and culture. It whispers that the quest to understand our place in the universe has always been a collective human endeavor, where the observations of one age become the building blocks for the genius of the next. So what was this cosmic calculator actually for? The answer is not a single purpose, but a layered one, revealing the interconnected worldviews of its time. For a philosopher, it was a teaching tool of profound beauty. The dominant Greek philosophical schools, from Plato to the Stoics, saw the universe as a cosmos, a word that means order and harmony. They believed the heavens moved according to perfect mathematical laws, a divine rationality that human reason could uncover. The Antikythera mechanism made this abstract philosophy tangible. By turning the crank and watching the bronze gears replicate the motions of the planets, a student could witness cosmic order in action. It was a physical proof of a philosophical idea, a universe governed by logic and ratio, not by the whims of temperamental gods. This mechanical model served as a powerful demonstration device. likely used in the lecture halls of Rhodes or the private studies of wealthy patrons to illustrate the very principles that underpinned their understanding of reality. Yet this philosophical instrument had an immensely practical and popular application: astrology. In the ancient world, astronomy and astrology were not separate fields, they were two sides of the same coin. Knowing where the planets were was the essential first step to interpreting their influence. A skilled astrologer casting a horoscope needed to know the exact positions of the sun, moon, and planets in the zodiac at the moment of a person's birth, or at the founding of a city, or at the start of a military campaign. Calculating these positions by hand using complex tables and mathematics was a laborious process that could take days. The Antikythera mechanism automated this. With a few turns of a handle, it could instantly display the precise celestial configuration for any date in the past or future. This was not fortune-telling, it was high-speed data processing. It would have been an invaluable tool for an elite astrologer advising a king or a general, allowing them to generate horoscopes and read celestial omens with unprecedented speed and authority. This predictive power bled directly into the socio-political realm. The ability to forecast eclipses, as the device did with its Saros dial, was a form of potent knowledge. In a world where an unexpected eclipse could be seen as a terrifying omen that might destabilize an army or a populace, the person who could predict it held immense power. They could frame the event, prepare the public, or even claim credit for appeasing the gods. The mechanism, therefore, was likely not a toy for the curious, but a serious instrument for the ruling and intellectual class, blending philosophical education with the practical arts of statecraft and social control. What about more mundane uses like navigation or calendar keeping? The evidence here is thin. While the device could track solar years and lunar months, its primary calendar was the stable Egyptian year, not the messy lunar calendars used for civic life in Greek city-states. It was not designed to announce upcoming festivals or agricultural seasons in a local context. As for navigation, its delicate construction and lack of any obvious features for measuring a ship's position or the horizon make it a poor candidate for a sailor's tool. It was a precision instrument for study, not for the rolling deck of a ship. Ultimately, the Antikythera mechanism's purpose was demonstrative and predictive. It served to illustrate the beautiful order of the cosmos, to generate the celestial data needed for astrology, and to forecast awe-inspiring events like eclipses. It was a machine built to comprehend time and sky, to reduce the infinite complexity of the heavens into a turning, tangible model that could be held in human hands. It served the needs of an elite who sought both to understand the universe and to harness that understanding for influence in the world below. For decades, the mechanism was a ghost in theory, its true form locked inside crumbling fragments. To bring it back to life, to hear its gears turn again, required more than just scans and translations. It demanded the hands of modern builders willing to step into the workshop of the ancient maker. The first great leap from blueprint to physical reality began with a historian of science named Derek de Solla Price. In the 1960s and 70s, long before the detailed CT scans existed, Price painstakingly analyzed the X-ray images available to him. He published a landmark paper, Gears from the Greeks, that proposed the first comprehensive model of how the device might have functioned. His work was revolutionary, arguing forcefully that this was an ancient computer for astronomy. But Price's model remained a theoretical sketch, a brilliant hypothesis waiting for a craftsman to test its bones. That craftsman arrived in the form of Michael Wright, a curator of mechanical engineering at London's Science Museum. Wright took a radical, hands-on approach. He decided to rebuild the mechanism not just on paper, but in metal, using tools and techniques as close as possible to those available to the original Greek artisans. He forged his own bronze sheets, cut his own gear teeth with files, and painstakingly assembled the complex trains. Wright's physical reconstruction was a dialogue with the past. As he built, he discovered things the scans alone could not reveal. He found that certain proposed gear arrangements would have jammed or created impossible friction, leading him to propose alternative, more elegant solutions. His working model, completed in the 2000s, was a triumph of experimental archaeology. It proved beyond any doubt that the device was mechanically feasible with ancient technology. Turning the crank and watching the pointers glide across the dials was a visceral, powerful experience, a direct connection to the ingenuity of 2,000 years ago. The latest chapter in this resurrection is digital. The International Antikythera Mechanism Research Project used the high-resolution CT data to create exquisitely detailed computer simulations. These digital models allow researchers to experiment endlessly, testing different gear configurations and astronomical theories with a click. They can simulate wear and tear or visualize the flow of forces through the gear train. This virtual workshop has revealed both the stunning brilliance and the subtle imperfections of the original design. The simulations confirm the incredible accuracy of the lunar mechanism, but they also suggest possible small errors in the gearing for the planets, hints that the maker was pushing at the very limits of his materials and knowledge. Each reconstruction, whether of bronze or binary code, serves as a test of our own understanding. They are questions posed to the original artifact. Does this gear fit here? Does this calculation match the inscription? With every model that turns successfully, the ghost of the ancient workshop grows more solid, more real. We are not just studying a relic, we are collaborating across centuries, using modern tools to answer the challenges its maker left behind. This level of mechanical sophistication did not reappear in the West for over 1,000 years. To grasp just how extraordinary the Antikythera mechanism is, we must step back and see it within the vast timeline of human invention. The ancient world achieved staggering technological feats, but they were feats of a different kind. Consider the Roman aqueducts, marvels of civil engineering that channeled water across mountains and valleys using gravity alone. Their genius lay in scale, logistics, and an intuitive mastery of hydraulics and stone. Or look to the Great Pyramid of Giza, a monument of almost unimaginable precision in alignment and mass construction. These are triumphs of monumental will, of organizing thousands of workers to execute a single grand vision. They are about moving earth and stone, about conquering space and defying gravity. The Antikythera mechanism represents a completely different branch of the technological tree. Its genius is not in scale, but in miniaturization, not in moving mountains of stone, but in moving ideas through the delicate interaction of tiny bronze teeth. It is a feat of information processing, a machine designed not to alter the physical landscape, but to model the conceptual one of time and celestial motion. For centuries after its creation, this specific path of technology, the path of complex precision gearing for computation, seems to vanish. The mechanical knowledge required to build such a device faded from the cultural memory of Europe. The medieval period that followed produced incredible machines, of course, water mills and windmills, the great clocks of cathedral towers, but these machines, while impressive, operated on a different principle. A cathedral clock might use a simple foliate escapement and a few gears to strike a bell on the hour, a magnificent achievement in timekeeping. Yet its internal mechanics were often crude by comparison, its purpose singular, to mark the passage of time, not to calculate the variable speed of the moon or the date of an eclipse decades in the future. The intricate, nested gear trains of the Antikythera mechanism, capable of performing multiple astronomical calculations simultaneously, would not be seen again until the astronomical clocks of the Renaissance, like the one built by Giovanni da Dondi in the 14th century. And even then, de Dondy's clock, a masterpiece in its own right, was created over a millennium and a half later. This gap is what makes the mechanism so profoundly disruptive to our historical narrative. It sits there, a lone data point on the timeline, a spike of advanced mechanical computation in an era we thought was defined by simpler machines. It forces us to ask whether this spike was truly an isolated anomaly, or if it is simply the only surviving evidence of a technological thread that was spun, used, and then tragically lost, leaving the later world to reinvent the wheel, or more accurately, the differential gear, all over again. The gears fell silent because the world that built them fell apart. The Hellenistic era, that vibrant fusion of cultures following Alexander the Great, was a golden age for the kind of knowledge that birthed the Antikythera Mechanism. It was a time of wealthy royal patrons funding research, of rival cities like Rhodes and Alexandria competing for intellectual prestige, and of scholars freely sharing ideas across the Mediterranean. This interconnected world of inquiry was the perfect incubator for such a hybrid masterpiece, blending Babylonian data, Greek theory, and exquisite craftsmanship. But this world did not last. Political unity shattered into squabbling kingdoms, and then a new power arose with a different set of priorities: Rome. The Romans were supreme engineers, but of a practical sort. They built roads, aqueducts, and siege engines, magnificent projects that served the state, the army, and urban life. They admired Greek learning and often collected its fruits, as the Antikythera device on a Roman ship proves, but they showed less interest in sustaining the deep, theoretical research that pushed that knowledge forward. The Roman focus was on application, on what worked, not necessarily on probing the fundamental mathematical mysteries of the cosmos. In such an environment, a fantastically complex astronomical computer became a luxury item, a dazzling conversation piece for a wealthy collector, rather than the focus of ongoing scientific development. The craft required to make it began to drift to the margins, sustained not by public institutions, but by a handful of private workshops. This is where the tradition became most vulnerable. Building something as precise as the Antikythera mechanism was not a common skill. It was a niche art, likely passed down orally and through hands-on apprenticeship within a single family or small atelier. The master would teach the apprentice how to mix the bronze alloy, how to lay out the complex gear ratios on a template, how to cut the teeth with file and saw to a tolerance thinner than a grain of rice. This was tacit knowledge, a feel for the material and the mathematics that lived in the fingertips and the intuition of the craftsman, not in a widely published manual. If that master died without a trained successor, if the workshop was disbanded due to war or economic hardship, that entire lineage of skill could vanish in a single generation. The knowledge was not lost because it was written down and then burned, though that happened too. It was lost because the living chain of people who carried it in their minds and hands was broken. The great repositories of written knowledge faced their own calamities. The famous Library of Alexandria stands as the ultimate symbol of this fragility. While its destruction was likely a gradual process over centuries, involving fires and periods of neglect, the result was the same. Countless unique texts, the compiled observations and theories of generations, simply turned to ash or dust. Scrolls containing the works of engineers like Ctesibius or Philo of Byzantium, who wrote on pneumatics and automata, disappeared. Treatises on advanced gearing or astronomical mechanics, if they ever existed, are gone. Each loss made it harder for the next generation to rebuild the edifice of understanding. So the disappearance of this technology was not a single event, but a perfect storm. It was the collapse of the political and economic systems that supported pure research. It was a shift in cultural priorities toward more immediate, practical ends. It was the catastrophic loss of written archives, and most insidiously, it was the extinction of a rare, hands-on craft tradition that existed in only a few minds. The Antikythera mechanism thus becomes a relic of a specific kind of fragility, the fragility of high culture. It reminds us that advanced knowledge is not a permanent possession. It is a flame that requires a specific and stable environment to keep burning, passed carefully from one set of hands to the next, or it will simply go out. The flame of the Greek mechanical tradition flickered, but did it truly go out? For centuries after the fall of the Western Roman Empire, the centers of learning and high craftsmanship shifted eastward. In the Byzantine Empire, the continuation of Rome in the east, and across the vast Islamic caliphates, the study of astronomy and the art of instrument-making not only survived but flourished in new forms. We find intriguing echoes, instruments that show a clear lineage from the ancient world, yet they also highlight the unique, lonely peak of the Antikythera mechanism. In the bustling markets and royal observatories of the medieval Islamic world, scholars perfected the astrolabe. This was a portable, flat disc of brass or bronze used for solving problems relating to time and the position of the sun and stars. Some of the most sophisticated versions incorporated simple geared mechanisms. These geared astrolabes could model the phases of the moon or find prayer times, a beautiful fusion of faith and celestial observation. They represent a direct thread of technical knowledge, a proof that the concept of using gears to model the sky was preserved and practiced. But these devices, while ingenious, were fundamentally different. They were analog calculators for specific, practical tasks. Their gearing was limited, often to just one or two functions. They did not attempt to create a comprehensive, moving model of the entire known solar system. Meanwhile, in Constantinople, the heart of the Byzantine Empire, a different kind of marvel arose. The Tower of the Winds, an ancient Greek structure in the Roman Agora, was later repurposed and topped with a legendary public clock. Historical accounts describe it as a complex water-driven automaton, showing the hours, the movements of the sun and moon through the zodiac, and even featuring animated figures that moved on the hour. This was a monumental public spectacle of engineering, a direct heir to the tradition of Heron's Automata, and a testament to Byzantine mechanical skill. Yet again, its purpose was largely demonstrative and timekeeping. It was a magnificent clock, an ornament for the city, not a portable computer for generating precise astronomical data for a scholar or astrologer. These medieval instruments are crucial to our story. They demonstrate an unbroken curiosity about the heavens and a continuous, evolving skill in metalworking and mechanism design. They show that the basic idea of using machines to represent cosmic order was never fully forgotten. But they also, by their very nature, underscore the radical outlier status of the Antikythera device. For over 1,000 years, nothing was built that combined its specific ambitions, its compact complexity, and its sheer computational power. The medieval world maintained the flame of celestial mechanics, but it was a steady, practical flame. The Antikythera mechanism represents a brilliant, concentrated flash, a moment when that flame burned with a different, more intense kind of light, focused on modeling the universe's deepest mathematical rhythms in a private, hand-held form. Its rediscovery forces us to see not a smooth, continuous line of progress, but a landscape with forgotten mountains. The silence that followed the loss of the Greek tradition lasted for well over 1,000 years. Then, in the steepled cities of medieval Europe, a new sound began to echo, the steady tick of a different kind of mechanical genius. By the 14th and 15th centuries, towering astronomical clocks were being built into the facades of cathedrals and town halls. These were monumental machines of iron and brass, driven by weights and escapements, their faces a riot of moving symbols. They told the time, of course, but they also displayed the phases of the moon, the position of the sun in the zodiac, and the movements of known planets. One of the most celebrated was built by the Italian physician and clockmaker Giovanni da Dondi. Starting in 1348, he spent 16 years constructing his astrarium, a planetary clock of breathtaking complexity. Driven by over 100 finely crafted gears, it had 7 separate dials to show the motions of the Sun, Moon, and the 5 planets according to the Ptolemaic system. It was a masterpiece of medieval engineering, a mechanical universe that rivaled the conceptual ambition of the Antikythera device. Yet here lies the most profound part of the story. Giovanni da Dondi and all the brilliant European clockmakers who followed had absolutely no knowledge of their ancient Greek predecessor. They were not rediscovering a lost blueprint. They were reinventing the wheel, or rather the differential gear, entirely from scratch. Their inspiration came from a different lineage, from the practical timekeeping of water clocks and the philosophical drive to see God's orderly creation reflected in machinery. The development of complex European clockwork was a parallel invention, a separate flowering of the same human impulse to model the cosmos in metal. This independent rebirth makes the Antikythera mechanism not just an ancient wonder, but a historical ghost. It means that for over a millennium, one of humanity's most sophisticated technologies simply vanished from collective memory. The European clockmakers, laboring in their workshops, were solving problems and achieving complexities that had already been mastered and then forgotten. Their triumphs were genuine, born of their own era's knowledge and tools, but they were walking a path that had been paved long before, then buried by time. This gap is what transforms the mechanism from a curious artifact into a profound cautionary tale. It shows us that progress is not a straight, inevitable line. Entire branches of knowledge can fall away, leaving later generations to believe they are pioneers in an empty land, when in truth they are rebuilding a lost city. The Antikythera mechanism shatters a comforting story we have long told ourselves about the past. For centuries, the history of technology was often framed as a steady, upward march from primitive beginnings to our modern mastery. In this narrative, the ancient world was a place of philosophical thought and monumental architecture, but not of intricate machinery. The so-called Dark Ages that followed were a period of stagnation, where such knowledge was lost or suppressed. Then came the Renaissance, a glorious reawakening, where geniuses like Leonardo da Vinci sketched wondrous machines and clockmakers began to build complex mechanisms, setting the stage for the scientific revolution and our computerized present. It is a clean, linear story of progress. The corroded bronze gears from Antikythera tear that timeline to pieces. This device forces a profound revision. It proves that the conceptual leap to building a programmable, analog computer did not happen in 14th century Europe or even in the Islamic Golden Age. It happened in the Hellenistic Mediterranean over 2,000 years ago. The sophistication we once believed was impossible before the Renaissance was not only possible, it was achieved. This means that what we often call the Dark Ages were not necessarily dark in the sense of a universal lack of capability. They represent, at least in this one branch of technology, a period of catastrophic forgetting. The story is not one of linear ascent, but of a brilliant peak, a deep valley of loss, and a long, slow climb back to a similar height more than a millennium later. This changes how we view every era. The ancient Greeks were not just thinkers, they were builders of information technology. The medieval period was not an empty void, but a time when different priorities and circumstances allowed one specific, advanced craft to fade from memory. The Renaissance was not a pure birth of new ideas, but in part a rediscovery of a potential that had always existed within human ingenuity. The mechanism challenges the very idea of historical inevitability. It asks us if this could be forgotten, what else might have been. It suggests that our current technological world is not the only possible outcome of history, but one path among many that could have been taken or retaken much earlier. This artifact compels us to replace a simple timeline with a more complex, branching map of human achievement, where brilliance can flare in isolation and knowledge, no matter how advanced, remains heartbreakingly fragile. Despite everything we have learned, the mechanism remains a puzzle with missing pieces. We possess only about 1/3 of the original device, a collection of shattered fragments. This means we are trying to reconstruct a symphony from a handful of surviving notes. Some of the most tantalizing gaps are mechanical. Based on the inscriptions and the layout of the surviving gears, researchers are confident the machine displayed all 5 known planets. Yet the fragments we have contain clear gearing only for the Sun, Moon, and the outer planets like Saturn and Jupiter. The delicate gear trains for Venus and Mercury, which would have been positioned on the front dial, are almost entirely lost. We can theorize their design based on the astronomical models of the time, but we cannot see their precise bronze teeth. The beautiful outer case, likely made of wood and perhaps adorned with decorative panels, is gone. The exact nature of the drive mechanism, the handle that set the entire cosmos in motion, is also a matter of educated guesswork. These physical absences mean that every modern reconstruction contains an element of inspired speculation, a best guess at the complete masterpiece. This leads to a larger, more haunting question. If this one device survived by the sheerest accident, lying preserved in a shipwreck, what else existed? Was the Antikythera mechanism the pinnacle of a line of such computers? It seems almost impossible that it was the very first attempt. The craftsmanship is too assured. Were there simpler training models for students with just a few gears to demonstrate basic cycles? Or perhaps there were even more complex versions, incorporating later discoveries or built for specific royal patrons. Could there have been devices dedicated to other forms of calculation, modeling the tides, or predicting the movements of specific stars for navigation? The silence of history is deafening on this point. These gaps are not failures of research, they are the very engine of it. Each missing gear, each absent reference in an ancient text, is a question that propels the investigation forward. They remind us that history is not a completed book, but a fragmented manuscript, and the most profound stories are often told by the empty spaces between the words. This profound silence begs a question that haunts every researcher. Could there be another one out there? The Antikythera mechanism was preserved by a perfect, almost miraculous set of circumstances. It lay in a deep water shipwreck over 50 meters down where the water was cold, dark, and devoid of oxygen. This anaerobic environment slowed corrosion to a crawl and prevented the wood and bronze from being completely consumed by marine life. The heavy sediment of the seafloor then encased it, forming a protective cocoon of mineral deposits that held its shattered pieces together for 2 millennia. For another example to survive, it would likely need a similar guardian, a time capsule that shielded delicate bronze from the ravages of time. Shipwrecks in the deep, cold waters of the Mediterranean remain our most promising hope. The ancient sea was a bustling highway, and the vessel carrying the mechanism was no ordinary trader. It was a luxury liner for art and intellectual treasures. Other ships of similar status, carrying elite goods and perhaps the prized possessions of scholars or nobles, could have met a similar fate, their cargo now resting in the silent dark. But shipwrecks are not the only possibility. Consider the sealed tombs of high-status individuals. In a culture that valued knowledge as the ultimate treasure, a device like this could have been a fitting companion for a philosopher king or a revered astronomer, placed in their final resting place to signify their wisdom. Such tombs, if undisturbed and located in stable, dry conditions, could preserve bronze and wood almost perfectly. The challenge, of course, is finding them. This is where modern technology offers a flicker of hope. Advanced marine survey techniques like autonomous underwater vehicles equipped with high-resolution sonar can map vast stretches of seabed in incredible detail, identifying anomalies that could be ancient wrecks. On land, ground-penetrating radar and other non-invasive archaeological methods allow us to peer beneath the Earth without disturbing it, searching for the outlines of hidden chambers. Each scan, each robotic dive into the abyss carries the potential for a world-altering discovery. The hope is not just to find another machine, but to find context. A second mechanism, even in fragments, would be a Rosetta Stone. By comparing its design, its inscriptions, even the workshop marks on its gears, we could finally understand if this was a unique masterpiece or a standardized model. We could trace its lineage. The lonely ghost in the Athens Museum yearns for a companion, not for company, but for conversation. Another find would allow these silent machines to speak to each other across the centuries, and in doing so, tell us the true story of the world that built them. That impulse to build a thinking machine did not die with the ship off Antikythera. It merely went dormant, waiting for its moment to reawaken in new forms. If we step back and look across the vast span of time, a profound conceptual thread connects those corroded bronze gears to the silicon chips in the device you are using right now. The Antikythera mechanism was not a computer in our modern, digital sense. It had no electricity, no binary code, and it could not be reprogrammed. Yet at its core, it performed the same essential function. It was a machine designed to process information, to take an input, in this case a date set by turning a crank, and through a predetermined set of mechanical operations, produce an output, the predicted positions of celestial bodies. Its gear trains were its hardware, the physical embodiment of its logic. The astronomical cycles and mathematical ratios, etched into the number of teeth on each wheel, were its software, the fixed program it was built to run. In this way, it was a dedicated analog computer, modeling the complex algorithms of the cosmos in tangible, turning metal. This reveals a lineage of thought far older than we often assume. The history of computing is not just the story of Charles Babbage's 19th-century difference engine or the code-breaking machines of the 1940s. It is a story that begins with a fundamental human desire to externalize our reasoning, to build tools that can handle complexity beyond the reach of our own mental calculations. The Greek artisans were doing precisely that. They took the intricate, multi-variable problem of planetary motion and found a way to automate its solution. They built a physical simulation, a universe in a box that could answer what-if questions about time and space. This is the same conceptual leap that drives modern computational science, whether we are simulating the climate, modeling the folding of a protein, or forecasting the path of a storm. We have simply swapped bronze for silicon and mechanical force for electrical pulses, but the goal remains unchanged: to create a working model of a system too vast or intricate for our minds to hold all at once. So, while there is no direct technological lineage, no workshop in ancient Rhodes that evolved into a semiconductor fab, the intellectual ancestry is undeniable. The Antikythera mechanism stands as a powerful testament to the antiquity of the computational idea itself. It proves that the dream of a thinking machine is not a product of the industrial age or the digital revolution. It is a timeless expression of human curiosity and ingenuity. When you use a smartphone app to check the phase of the moon or see a visualization of a solar eclipse years in the future, you are engaging in a dialogue that began over 2 millennia ago. You are witnessing the latest chapter in our enduring quest to not just observe the world, but to build a mirror for its logic, to hold the patterns of existence in the palm of our hand, and finally understand the clockwork. The Antikythera mechanism is more than a single, miraculous artifact. It is a window, a tiny, clear pane of glass through which we glimpse an entire lost culture of technological ambition. This intricate bronze computer was almost certainly not a one-off wonder conjured from nothing by a solitary genius. Its perfection speaks of a tradition. The assurance in its design, the flawless execution of its gear teeth, the deep integration of complex astronomical theory, all of it points to a workshop, a school, a lineage of knowledge. This device is the sole surviving representative of what we might rightly call a lost era of Greek computing. It is the last known whisper of a conversation between mechanics and mathematicians that flourished for a time, creating machines to model reality itself before that conversation was tragically cut short. Its lonely presence in our museums forces a humbling realization. Our map of history is not complete. We have been charting a landscape with entire mountain ranges missing because the peaks crumbled into dust and left no trace. The story of human ingenuity is not a smooth, upward slope. It is a terrain of brilliant, isolated peaks and deep, silent valleys of forgetting. The Antikythera Mechanism is proof that a civilization can climb to a breathtaking height of sophistication in one field, only for that knowledge to vanish so completely that later ages must begin the climb all over again, believing themselves to be pioneers. This changes everything. It means our understanding of the past is always provisional, always subject to revision by the next discovery in a shipwreck or a sealed tomb. It asks us to hold our narratives lightly, so as we leave this ancient computer and its echoing questions, consider this final thought. If something this sophisticated could be lost for 2,000 years, what else might still be out there, hidden in the earth or resting in the deep? What other marvels, what other chapters of a forgotten human story are waiting for their moment to be found, to step out of the shadows and rewrite everything we thought we knew?